Hello, everyone. My name is Fuad Rahman. I'm presenting this paper on behalf of our team at Goldman Systems. And the title of the paper is Disease Modeling with a Forest Deep Neural Network Utilizing Natural Language Processing and a Virtualized Clinical Semantic Network. It's a long title, so I better get started. The bigger picture that we want to talk about is, what one of the biggest issues in healthcare right now, and then we're going to focus on something more granular, which is modeling diseases, and then we actually talk about specifically what we are presenting in this paper, which is how we actually model influenza, and then we're going to talk a little bit about the tool itself, the forest deep neural network that we have used. And then we're going to talk about some performances and draw some conclusions. So what's the bigger picture? The issue with our healthcare system right now is that it's really fragmented. Data is coming from different directions. It can come from electronic healthcare records, claims data, labs data, all sorts of different places. And the categories of that is also very diverse. It can be in any different categories. It can be in clinical side, can be in social determinant side, can be health and wellness side. The problem is that there is no end-to-end mapping. There is no exact mapping between these two sources, right? And mostly the mapping is one-to-many or many-to-one, and that's part of the issue of this fragmentation that we see. The issue that we have is that most of the data, in some statistics say up to 80% of the data that we have in the clinical healthcare system recorded as part of our healthcare system is actually textual. It's not numerical. So understanding that data and doing anything useful with that data is not that easy. As we all know, the data is great, but without context, it doesn't really help us that much. And as we all know this very well-known pyramid where data gets into information and the information gets into knowledge, and eventually we can do something about it. So what we want to talk about today is how do we get data, useful data, computable data from textual and non-textual sources specifically for healthcare, and then how do we then go get it into an informational level so that the interoperability goes up and the human effort goes down, as you see in the left side of this pyramid. And the way that we think we can do this is by adding contextual information in terms of the semantic query. If we know what data means and how that data is connected with different types of other data that is interrelated, that semantic querying is actually the way to go. And we're going to talk about this a lot in this presentation today. So the next step of this is, what do we do with this particular, if we are able to do this, what can we actually do with this, right? So let's talk about disease modeling. Today, we want to talk about disease modeling specifically. And there are roughly two types of disease modeling. One is, mathematical disease modeling, which we mostly are doing here. But then obviously we have clinical disease modeling, which basically augments what we can do from a mathematical side, and then adds a lot more insight into what we actually can get. We are today going to be focusing mostly on the mathematical side of disease modeling. So let's be a little bit more specific. What kind of disease modeling we're looking at today? We're looking at modeling influenza today. And the influenza itself is a very comprehensive disease. It's very common, and a lot of us ignore it. But if you look at the statistics, it's a hugely problematic healthcare issue in the US and the rest of the world. I mean, it results in over 30 million outpatient visits every year. That's a huge burden on our healthcare system. So if we are able to somehow take a look at pre-existing healthcare data and can predict what kind of, if we can predict if a particular patient is more vulnerable, for influenza, for example. That itself is a huge advantage in handling at the policy level and at the intervention level these diseases. So let's not talk about what we actually did. So we chose a tool called Forest Deep Neural Network. It's a neural network that obviously has a forest layer for pre-selecting the data. But before we actually go into that one, that description, I want to talk a little bit about how do we actually take textual and non-textual data into our model, because that's very, very important. And the primary tool we use there is a semantic network that we call Clinical Semantic Network, or CSN. And it's basically a combination of diseases, interrelated and interconnected in a relational kind of relationships, and also findings, which we call common values. Now, these two together, the so-called D numbers that we call, and the F numbers as we call, they actually can together give us a very detailed explanation of tagging mechanism of this data. And that's the primary network that we have used. What we have done is we have actually virtualized this healthcare taxonomy. And we are now able to scan through textual data and can find the closest clinical concept within that taxonomy. And that itself makes the process of text to numbers, right? Which then obviously can put into a neural network kind of system. And that's kind of the crux of our presentation today. How do we take textual data and then mix it with non-textual data? Now, an overall schematic of this entire process is in this slide. And as you can see that we can take data from different sources, textual and non-textual. And then we actually go through a pre-processing of state of tagging. And that's basically the vCSN step. And once we actually have that, then we actually can push this data into some sort of a neural network, right? Some sort of a discriminatory network. And that can then be saved for down the stream processing. And is this third step, or the models that we're going to talk about today. One of the models that we have used is this deep neural network, this Forest Deep Neural Network. Now, a detail about this, this is only a 15-minute presentation, so I won't be able to go into detail about it. There are plenty of details in the paper you can go and read. But sufficient it is to say that the forest is, or the random forest layer is basically used as a way of pre-selecting the variables. And once we have that, it is then encoded and then pushed into the deep neural network layer. And that helps in actually getting better discrimination from the deep neural network. Let's talk a little bit about the sources of data, because we have data coming from many different sources. And we have structured data, which is numerical data, and unstructured data. So for example, we have visit information, detailed visit information from patients. We have vaccination reports, we have time measurements, procedure names, diagnosis, allergies, and a lot more. And we're going to talk about that a little bit more. And they're of different types. So some are singly type, and some are composite types, and some are hybrid. So what we have done is we have actually mixed them to see which gives us the better discrimination in the network. And in terms of the data, and you can see this is actually again going back to the details of the deep neural network. It actually shows the parameters at the different layers of the network. And this slide shows the number of neurons that are being used in different hidden layers. So given all this, what do we actually see? Let's take a look at some performances. So the data that we have used have actually come from a big East Coast-based healthcare data system, and we are under NDA, so I can't use the name. But the total number of samples we had about 3,100 patients' data we had. Roughly half of them were used, actually exactly half of them were used as positive data samples, and exactly half were used for negative data samples. 85% were used for training purposes. Now, what this means is that all the data, all the results I'm going to show you today are actually on unseen data. I'm not showing you evaluation data as some presentations have done. I am actually showing you data results on unseen data, though that 15% that we have used. And this chart gives you kind of like a summary, and there's a lot of information here. I'm not going to go into detail, but as you can see that we have tried both bag of words and TF, IDF encodings, and the results obviously vary based on what we have chosen, but probably not a lot. But the more important thing to take a look at here is that the accuracy is in high 90s for some of these combinations, which is extremely encouraging for a very complicated task like the one that we're handling right now. And this slide shows in terms of the validation loss and the training accuracy, and you can see they track fairly well. So the models are probably not overtrained or undertrained. For illustrative purposes, we're also showing some the best performing models and the worst performing models using different type of vectorization and encodings. Let me zoom through it because I'm running out of time here, because I want to talk a little bit about the timing factors. As you can see in this slide, the different type of data takes different type of time, obviously, and obviously visit takes longer because it's purely textual. A lot of it is not, which it results in much faster training times. And the other thing that we see is that depending on whether it's TF, IDF, or bag of words, even visit is still the slowest, which is we expected to see anyway. And same thing is repeated in this slide. So let's run into a little bit of discussion and conclusion because I have about 2.5 minutes left. So what we have observed here is that we can actually get fairly good results from this data, but the best results are actually achieved from the hybrid networks, and that kind of tells us that the use of semantic queuing using the CSN and then vCSN has actually given us the power to actually digest the relations embedded into the textual and non-textual data, and that has proven to be very effective. And as I mentioned before, we didn't really see a lot of difference between the type of encodings, and we were not really expecting to see either. So in conclusion, let's draw some conclusions here, is that we think we have actually shown that for a very complicated task, such as predicting a disease, like an onset of a disease based on pre-existing clinical data, which is itself is by its very definition is a very, very complicated task. We were able to predict with very high confidence and accuracy the onset of influenza based on at least on our data, and we think that the use of a forest layer in terms of the pre-tagging and pre-clearing of the variables in the early stage has really changed the way the results have come. So in future, we would like to use this for other type of diseases. We actually have recently come across, have received some data for COVID, and we would actually use this model on that COVID data. And we would like to see what kind of generality we can actually get from this kind of models. This is something that the work is currently undergoing, so I don't really have anything to share. But just to give an idea that we'd like to see if we can make this kind of networks for predictive, at least for predictive, applications, a more trainable model. Because if we can make this easily trainable especially without human intervention, then that's actually the best way of going. So thank you so much for your attention today. And I'm going to be live here to answer your questions. Thank you so much.